Okay, hi everyone. I'm going to just start with a little story about a system that I built in a previous for a previous employer, previous company. And very simply, there was the system is like an online application for what in the UK we call DBS checks. So if you're going to work with young children or vulnerable adults, vulnerable children, you have to have checks done against your background. So scout leaders, teachers, all of that sort of thing. I'm sure there's probably something equivalent here as well. This process was we were working for a client where they recorded this information electronically online through a web page, and then sent that information off to the government, and then you'd receive a response. The process kind of goes like this. The user completes an application form. We then, the application form typical of your personal details, where you lived, and so on and so forth. Then it goes off to for a verification process, or a group of people go and check that the information that you've entered is all correct and sound, so that we don't get a rejection from the government, as it were, just because you haven't completed the appropriate amount of the appropriate history and so on and so forth. Typically, once a user has completed the application, a lot of the users are working from screens where they're seeing lists of information, and those lists are aggregating lots of data about users, which is all stored in different locations. This is not actually from the system. I've just got something that kind of gives you an indication as to what it was. So after the verification process, a result is received, and then the applicant is informed as to whether or not they can work with children. Now, our architecture, it was a kind of a typical 3-layer thing where we've got a front end, it goes through some business logic, and then there's some data access. I think most people have seen this in the past or worked on things like this. But for tonight's talk, what's really important is to understand this bit here, in that we had a very heavily normalized table schema, as you would do in when we're saving data, for example, in SQL Server. Addresses were in their own table, names, because we had to capture history of people's names, were in their own table, represented by a contact, and so on and so forth. Very heavily normalized table structure. Now, it was a very successful product, and for that company, they were bought up by a larger company that had a portfolio of these types of products, and a very, very successful project for us. However, as time went on and the customer requested more and more features, we delivered those features, but we never really paid attention to scale. And the customer would now and again receive reports from users that this is taking a little bit long. But the thing was that the end users weren't actually experiencing many of the scaling issues, because their job was very simple. They completed an application form and submitted it. It was the back-end users that were having trouble, because they were seeing these aggregated views, these lists of people, and they would want to search by names, addresses, maybe job roles, and it was becoming more and more difficult to narrow down the list of patients, and in that grid-like view, it was becoming slower and slower. But we continued, as any sort of consultancy does. We were given work to do, and yes, we'll build these new features, we'll continue, until it came to a head. And my talk tonight really is about that experience and how we stumbled into the CQRS pattern. Because it wasn't something that any of us within the team knew about, but we'd kind of come to a solution that was a very CQRS solution. So I'm just going to talk a bit more about that system and what we did to improve that, and then a little bit about what is CQRS and its history, and then I've got a bunch of what I call recipes for how maybe you could take a similar type of application, or people talk about monolithic applications, or an application that maybe has a single store of data, and then you want to scale it out. What are some of those approaches that we can take to thinking about scaling out applications? This is the only silver bullet in the room tonight. So anything I talk about and I give, it's quite easily standing here, it can sound like this is the way to build all applications or what have you, but it's not. In the scenarios that I'm presenting and talking about, yes, it worked for us, and different situations might find that other architectural patterns are better suited for that, for those contexts. So once we came across some of these issues starting to come to a head now, once we were at that point, the customer's not happy, really, this list is now unusable, we can't really search for data, things time out, we could increase the timeouts for our queries and what have you, but it's not really a solution. We really need a solution to this. As good developers do, we start looking at the tools that we're using. Maybe we could replace the ORM because we were actually using Link to SQL, and maybe we could switch to Hibernate or Entity Framework and leverage some of the features inside of that. That was maybe one approach. Caching is another approach. Maybe the data doesn't actually need to be as up to date as real time as we might have initially thought, and so caching is actually a really good option to maybe introduce a layer in there. And sometimes that can be done with very little code changes, with something like, for example, like ncache. You can just plug a caching layer into your .NET type application. I'm going to talk about, I should have said maybe in the beginning that most of my experience is through .NET applications, and so that's the kind of stack I'll be talking about. Inevitably, somebody does then say, yeah, let's do a big rewrite. Let's re-architect the whole system, and it will be faster and it'll be better going forward in the future. And all rewrites promise to be that, and they also promise to be done in a certain amount of time, and they never, expand. They never take longer. Sometimes an easy option is just to throw more hardware at a problem. And that can only get you so far. A bigger box for your SQL server, but then that might also be, add more cores and more licenses and what have you. It could be very costly. But then nowadays, bigger servers, somebody else's servers use them in the cloud, and scale up a database just using a slider, for example. With any of these type of approaches, and because I'm a contractor, my answer now would always be, which is the right approach? It depends. It depends on a number of factors. So what we began to do is we began to optimize our Link to SQL, trying to find optimizations in the queries that we were building. But we soon discovered that actually there's only so much that we could leverage from that because of the schema, because of the data structure, because this is where we were writing information to, and then this is where we are also reading information back, as in reporting, creating reports and displaying them back on the screen. The idea that we had was, well, maybe if joining on all of these tables is the problem, maybe if we introduced a single table that had all of the information that we were searching on and have that just in a single table, there would be no reason why that would be immediately quicker than joining on all of those tables and then reporting back. So quite simply, we created an application search table with the fields that were most important, and then a reference back to the user's application. And it was like day and night in terms of performance. This table, we would update this table using SQL triggers, so that the original columns in the name table, the address table, if anybody made a change there, it would then go and update this table. And it was a very simple solution, but a very effective solution. And so now the hesitancy that we did have moving forward with this solution was, well, are we not now duplicating data? So we've got a user's name in this application search table, and we've also got their name in the original table. And there was some real, what's if the data gets out of sync? It's a big problem. We were relying on these SQL triggers to correctly update this denormalized table, and hoping that everything was going to be okay. So denormalizing that data was the solution here, and at the time we never knew, but this is in this realm of CQRS type of thing, where the idea that maybe where we write information to doesn't necessarily have to be the same place where we read information from. And so the thing that we're noticing here is that we have data, but it's used in like these two different types of ways. We write to it, we write to our data store, and then we read it back for various purposes. Sometimes we read it back to make sure that when we're writing data, that the data is consistent. Other times, most of the time, we're reading data back to present in a like report type format. Even though it might not be called a report, it might be a very real-time view of the data in the database. But it's these two type of operations. And so then that leads us on to our subject at hand here today. So CQRS originated, or the pattern that kind of preceded it, is a pattern called command query separation. And quite simply, the command query separation describes, simply says that every method within your system is either a method that changes the state of your system or queries that state back or returns some data. It's a real simple pattern. You either change data or you read it back, and those operations should be reflected in your method signatures. So for example, if we have a bit of C# code here, I hope everybody can see it towards the back. We have a bunch of functions here that, for example, you will see, let's see if you can, sorry, I'm just going to see if I can highlight this. Yeah, so for example, this submit, approve, reject, these are all functions in this particular class that make some changes to the system. And then down here, we have a get function. It's going to return some information. So we have these two types of operations here. And CQRS simply guides us to adjusting these signatures ever so slightly so that so that we can communicate that information. So in maybe a very pure interpretation of CQRS, you would say that the functions that change the system and the functions that return the system, the method signatures are adjusted. So for example here, the ones that change the system, they have no return type because their only function is to change the system. And the functions that return make no changes to the state of the system, so there are no side effects as a result of calling these functions. That's really, really important. So so all they can do is to query the system, return data. And quite simply, that is it. CQRS even simpler is to say that, well, these two types of functions, let's host them separately. So in my example here, I've now split them into two different classes. And quite, in its essence, it really is just that. Just separating out these functions. So all of my, what I might now describe as commands, because they are written in a way that describes the change that's going to be made to the system, is hosted in one class, and all of the functions that we can use for reading are hosted in a second class. And that's quite simply the CQRS pattern. Functions that change the system, functions or methods that return data without making an effect on the state of the system. So commands is what the term that that we use, or we might also then substitute the word writes for it. These commands describe the intent of the change that's required to the system. So a submit application, a reject application, approve application, these type of imperative words that we see. And each command has we notice that each command represents usually like a use case as well, and it has almost a one-to-one mapping. This is where you will find all of your the business logic, because it's when you're making changes to the state of your system that we want, because at the end of the operation we want consistency. We want consistency in our data, and the consistency is enforced by the rules that the business places upon us. So when we go to approve an application form, then there are certain rules, maybe who can approve that application, whether that application is ready to be approved, and so on and so forth. All of these rules the business will dictate to us. And so in these set of functions that are commands, that represent our commands, we'll find all of our business logic there. When we're reading back data, other than maybe things like access, like who has the rights to view this data, you won't find those type of business type of rules there. And maybe the only other point I want to mention about the reads or the queries, the methods that return data, is that usually what we're going to now find is that the shape of that data will reflect how it's going to be consumed in the front end. So you can now start to return data which is in a better shape, like for example in the application search table that we created. That data is now shaped in a better way so that on the screen it kind of closely matches the way that it needs to be presented on the screen, and doesn't have to go through this layer of translation or joining together, aggregation, before it's presented on the screen. Because that process of aggregating that data, even if it is joining 2 or 3 tables, as we start to move into hundreds of thousands and millions of rows, it's a problem to aggregate that data on the fly. So a reminder of this kind of like architecture that we had. We then, with a CQRS style, we can now that we've separated our methods that are writing and the methods that are reading, well, we can now maybe change the shape of this architecture ever so slightly, so that the methods that change data, which sit on this side, kind of go through one stack, and the methods that read data can go through a different stack. And so now you're starting to see maybe how the principles of CQRS can the principles of CQRS can then start to help you think about the technology stack that you're using to service these two sides here. So now I think so this side here is the command stack, this is the read stack. Now I'm going to run through a few recipes, what I call some recipes, about how maybe we could look at leveraging this type of approach. Now the first one is I've called it separating your ORMs. So maybe typically I have made an assumption that you're using an ORM, something like Hibernate Entity Framework, to do all of your read and writes. But but it could be substituted with ADO.NET, whatever you're using to as that layer between your code and the database and getting data to and from the store. So the first step, once we had kind of realized that we could do the have a table specifically for reading and then our write tables, is that we could then actually optimize our ORMs so that we can optimize one for writing and one for reading. The one for writing may be, you could implicitly wrap transactions and all of that sort of thing around them. The optimization for the reading could be things like, for example, within SQL Server, you could add things to your connection strings to enable like a read-only connection string, something that would make better use of connection pools and things like that, whereas that might not make sense for when you're writing, for example. So this one is a very, very easy optimization, and once you've kind of split your methods as I described earlier on, once you've split them in them two different locations, so you've got them in two different classes, applying something like this is really, really easy. So you could have something like this, where we have a class which represents our read operations, and inside of here I've got I'm using an optimized SQL Server connection string. That's all I'm doing, and then I've got an entity framework context which I'm instantiating. So that might give us a little bit of performance benefits. So when we're reading this data, it could be maybe slightly faster to read. You could also then use, you don't have to use entity framework then. So if we were using link to SQL for both read and write operations, we could dump the link to SQL implementation and use something like Dapper, which is a very, very thin micro ORM as they call it. So, and again, this is just an example of maybe how I could use Dapper. Yes, I have a select star. You wouldn't normally do that, and you would list the columns that you would actually need. But I've now started to make some micro optimizations in how the data is being read back. Recipe number 2, the next step I could now do is, once I've got this separation, I could then maybe leverage features within my database and take advantage of the fact that data could be read a little bit quicker. So for example, within SQL Server, rather than writing queries directly against tables, I could create something like an indexed view. So then SQL is doing some optimization for reading back that data, and so this one is another easy step in terms of the process of optimizing. And so here, the only change here is that now I have a view called v all applications, and this is an indexed view. And so when I call that, SQL has already created done some optimization so that when you read that data back, it's quicker. And so there may be other things within SQL Server that you can also leverage, but these are like very, very quick wins. There's no need to really re-architect your application, and this kind of approach gives you a lot, I believe, for your money in a short amount of effort, but some potentially big gains. The next thing now is a little bit more intense, or a little bit more invasive. We can now maybe start to think about our read side of the data, the read stack, if I might call it that, and think maybe actually is something like a relational database the best choice for that. So maybe what we might want to do is to store the data in a shape that would make it easier to read back, similar to what I had done in my previous example where we have a denormalized table. So you could still continue to use SQL in this way. You could have another table that represented another view on another web page, for example, that where the data that was being presented on the screen matched the data, or the data in the database in that table matched the data that was being presented on the screen. You don't have, there's no reason why it just has to be one. You could have many of these views of data. And this could take place in SQL, but then again, it could also be done in something like Elasticsearch, a document database, RavenDB, whatever. It gives you options where you could actually change that whole stack. Now, the issue there then is, so if we look at back at our architecture again, we then start to do something like this, where we are writing data to where we've always been writing data to, but then what we're doing is we're creating something called like a read store, or we have a database or some tables, or maybe even a different piece of technology that is being used to read data from. Now the problem there is, well, how do we get data from our write store over to our read store? How do we push that information across to there? So you can there are four strategies for doing that. And first of all, what you could do is you could take the approach of an on-demand type of strategy, so that when I make changes to my write store, immediately in the same operation, I will update my read store. So in my first example, the system that I was talking about, I make a change to my name table, the SQL trigger then goes and updates the denormalized table. That's quite simple. That's that first. So on demand, part of that same transaction, everything's synchronous. Problem there could be that, well, when the user's making that change to the system, it might take a little bit longer for the transaction to persist, because we're not only updating the write store, we're also updating the read store at the same time. Now, in a low volume system, that you'll get away with that. In a high volume, high transaction system, maybe not so. Now, in the example I gave, the system I was working on, regardless of the volume of applications, regardless of the number of applications they are managing in the system, they are never always at one particular time. So they were very spread throughout 24 hours. People could complete their applications whenever they wanted, and we never really had to think about an asynchronous style of handling that. So that's perfectly fine. Let's say a ticketing application. No, you would not. You would, if you were selling tickets for a concert, for example, you're going to get a high volume at a particular time, and that's obviously going to be a problem. So maybe the on-demand might not be the right strategy there. The next one, the next one could be a scheduled task. So on a time basis or some other event, you can update your read store, but it doesn't necessarily have to be part of the transaction when you are writing to that store. So I don't know, let's say every night you update the read store because somebody is only interested in a view, an aggregated view, the following day. They're not interested, it doesn't need to be real time, or maybe even on an hourly basis it can be out of date. Perfectly fine to do it on a schedule. The third approach is now where we start to move into for example, like an asynchronous approach. So we've made the change to our write store, but then we fired off an asynchronous request to go and update our read store. That's great for the user making the change to the system, because then they don't have to wait for that change. But now it introduces a little bit of complexity, because what happens if that change isn't successful? We'll now have a little bit of inconsistency between the write store and the read store. We will also potentially, let's say for example, because it's an asynchronous process, there may even be a delay in when that change persists. And so we start to then talk about something called eventual consistency, or it will eventually be up to date. It'll take a little bit of time, but that time period is then going to be discussed with the business. What's acceptable? You know, I don't know. I think a lot of the times when you talk to business people, you might say it'll take up to a second. Oh no, you know, even a second might seem too long. But when you think these things through, and how people, I don't know, somebody takes an order on a telephone, puts it in a system, and then, you know, people file paper here and there. There's things in the real world that take time, and at the conclusion of those events in real life, if the system's up to date in that amount of time, 10 seconds, maybe 15 seconds, it's no big deal. The fourth approach is a synchronous approach. And again, our command is so it's very similar to the other one, but everything's still going to happen in terms of the same transaction. So these are sort of 4 strategies for synchronizing that data between your write store and your read store. Now, I have a 4th recipe here, and that's because this 4th, now that we've separated our code into sort of 2 distinct functions where we're writing and reading, it opens up an opportunity to think about how we are persisting our data, the write stack now. So if, for example, we took now the approach, rather than maybe taking the data and normalizing the data and then saving it nicely into these different pots of storage, you know, these different tables. What if we took the data and saved it as an event that occurred in the system? So, for example, approve application, and I then saved just that approve application as I save that data as what's called an append-only stream. So as the changes come into my system, what I'm doing is I'm saving those changes as the user has requested them in a move forward type of database. This is what we call like an event store. And so what we're doing is, as the changes come into the system, we're not translating that data into a nicely structured set of tables, but what we're doing is we're saving the changes as the user has requested in the system. Now, why might you want to do that? For example, so right now I work in healthcare, and we have an event source system. So what we do is, as things happen to a patient in the system, what we're doing is we're storing those different events that take place. So a patient is admitted to a ward, a patient is then transferred care, i.e. the consultant for the patient changes, a patient has just had some observations done to them. So what we're doing is, instead of taking that data and then updating the patient table and the patient history table, we're actually just storing the fact that this patient and this event occurred, and this is the other bits of information that we need for that patient. What we can then do is we can use that information and almost replay that information to create our read models. And so this is quite a difficult approach. This is quite a challenging architecture or way of organizing your system. And if I go back to this example, this architecture that I showed before, the way that it changes now is we talk about commands coming into the system, and so then we can store those commands as this append-only stream, and then from that we use something called projections to create different read models, so that then those read models can be consumed wherever they need to be consumed. this is quite a challenging way of architecting the data, but for some scenarios, quite well. When you think about a lot of systems that you can work on, you can actually think of systems in this way. There's a series of events that take place, and sometimes one after the other, sometimes it's maybe a little bit more complicated like that. But within healthcare, accountancy, for example, an accountant, as they make a ledger, for example, they will continually, they don't go back and change a set of accounts, but what they'll do is they'll add on to the set of accounts the change that needs to be made. So if there was a problem in an account and we needed to make a correction, we would add on to the end what the correction is, rather than going back and making the change. Now, this talk really isn't about event sourcing, and that's why I'm really light on kind of describing what event sourcing is, but it's really to kind of give you an indication as to this is what's possible when you take the CQRS pattern all the way through to the end. But I believe that there's a lot of benefit in the earlier recipes that we can use and utilize in helping our applications scale as time goes on. And so then when we think about those big rewrites, we are maybe we could think about moving in small steps that actually would get us a lot for our money, for the effort that we put in initially, than to move to something as dramatic as an event-sourced system. Okay, so that's everything that I have for on this presentation. I hope that's of benefit.